This is slide number 14 and I am your presenter Asloob Mudassar. You know that from the previous slide we have calculated the vector P naught to P, and here we are again calculating it, where R is the position vector of the point P and R naught is the position vector of the point P naught. Position vectors means that these two vectors are referenced with respect to the origin of coordinate axis. And I have written the vector on the right hand side x minus x naught into unit vector I plus y minus y naught into unit vector j plus z minus z naught into unit vector k. So you see that now we can write the plane wave of profile e to the power iota k dot into that vector p naught to p. And this is given by, if we substitute the upper value over there and write briefly, that is, if you replace p naught to p vector by r vector minus r naught vector, then you can write e to the power iota k dot r naught and e to the power iota k dot r. The term exponential term e to the power iota k dot r naught is a constant term, and we can disregard the constant terms. Whenever we write the plane wave, we can drop the constant phase vectors or any constant terms. That would not change the physics. So we ultimately get the plane wave of profile as e to the power iota k dot r. And you know that this does not involve any time. So we can say that this is the profile at a time t is equal to 0. Now you see that this is the profile. Profile mean at static time. If you want to convert into a traveling wave, what you have to do is that you have to replace r vector by r minus vt. So this is what we have made the changes, and we have written down that the traveling wave of profile is equal to e to the power iota k into r minus vt. So evaluating this one, we have written that e to the power iota k r minus omega t. In the writing this one, we have calculated the cross dot products. K dot r is equal to k r cos of theta, and you know that here the angle between the k vector and the r vector is very approximately equal to 0. So we have cos 0 is equal to 1. So we have written k dot k and r, and you know that we have k dot product with v will give you omega. So we have e to the power iota k dot k r minus omega t. So this is actually the profile of the traveling wave, and of course here t is not equal to 0. Now you know that we know that the phase vector, which is k r minus omega t, is a constant in a wave. So at any time this is constant. So we can write k r minus omega t is equal to constant. And to keep this factor constant, that is k r minus omega t is equal to constant, you know that when time will increase, to keep this constant r has to increase, because the negative terms is with the time. So when the time will increase, the negative term will increase, and in order to compensate that one, the r must increase in the positive direction. So you see that r must increase in the positive direction. It means that this wave, which we have written as a traveling wave e to the power iota k r minus omega t, is a traveling wave which is propagating in the direction of increasing r. If we write the plane wave as e to the power iota k r plus omega t, that is, we replace the negative sign with the plus sign, then you know that k r plus omega t has to be constant. So when time will increase, the term with the time will be increasing in the positive direction. So r in that case must be increased negatively, so that the product, that is so that the term, that is k r plus omega t, should remain constant, and in that case the traveling plane wave will be traveling in the negative r direction. So this is what we have written about the profile of the wave and the traveling wave. So if you put t is equal to 0 in the traveling wave profile, then you will get the plane wave profile, that is the profile of the wave at some static time t. In Fourier optics, only the profile of the plane waves will be used for the purposes of a field calculation. We shall not be using the expression of the traveling wave, but we shall be using only the profile of the plane wave in order to calculate the field from one point to another point in our optical system. So in Fourier optics, the profile of the plane wave is important for us, and we have written that profile there. And you know that we have involved only single wavelength. This is strictly for monochromatic light source, as the analysis involves only single wavelength. Now you know that in the previous slide we have written the wave profile as e to the power iota 2 pi into fx into x plus fy into y. So this term is also equivalent to the e to the power iota k dot r. Both are equivalent. The only difference is that if we substitute the value of fx and fy from the previous slides, which were respectively cos alpha over lambda and cos beta over lambda, if you substitute these values over there in the fx and fy, and then you write 2 pi over lambda is equal to k, and k cos alpha and k cos beta can be represented as vector k, and xy can be represented as vector r. So you will ultimately get e to the power iota k dot r. So e to the power iota k dot r and e to the power iota 2 pi within the bracket fx into x plus fy into y, these two are equivalent profiles of a plane wave. So here you know that this is the end of slide number 14.